Hello, this is the pre-lab lecture for the Conjugated Systems Lab in Chemistry 246. The first part of this lab is going to be setting up a Diels-Alder reaction. The Diels-Alder reaction takes place between a conjugated diene and a dienophile. Dienophile is usually an alkene. Usually this reaction requires heat. In our case, the reaction is so favorable that it takes place at room temperature. In the end, you get a cyclohexene as the product. Here's the specific reaction that we're going to perform. We're going to mix furan as our conjugated diene with maleic anhydride. Furan is a cyclic conjugated diene. Whenever you have a cyclic conjugated diene, you're going to wind up with a bridged product and two possible isomers of that product. If the bridge and the dienophile are pointing in opposite directions, that's known as the endo product. If the bridge and the dienophile end up on the same side of the ring, that's known as the exo product. Which product you get depends on the reaction and the conditions that are used. The endo product is known as the kinetic product. This is because it forms the fastest. However, due to sterics, the exo product is actually the more stable product. If this forms, it's known as the thermodynamic product. Most books will tell you that the kinetic product is more common. This is the energy diagram for the reaction that we're performing. The orange line is for the endo product. You notice that the hill, which is the activation energy, is lower for the endo product. The lower the activation energy, the faster the reaction takes place. The blue line is for the exo product. The activation energy for the exo product is higher. However, once you form the product is lower energy and more stable. This product can form if the reaction is given enough time to equilibrate into the more stable form. To set up this reaction, we are going to dissolve maleic anhydride in ether and then later add the furan. If you can get it to dissolve without warming, that's fine, but usually it helps speed things along if we warm up that test tube to get it to dissolve. We're going to do this in a warm water bath. You should look up the boiling point of ether as part of your notebook preparation, and you're going to want to keep the water bath below that temperature. You don't want the ether to boil over. You also don't want too much of it to evaporate. We're just using this to dissolve the maleic anhydride. Now, if you set the hot plate to exactly the boiling point of ether, it's going to take forever for that water to warm up. So you probably want the hot plate warmer than that, at least at first. However, if you have the test tube of ether on the hot plate, you are going to want to keep the hot plate below the auto-ignition temperature of ether. If ether vapors hit the hot plate and it's above that temperature, the vapors could spontaneously ignite, and we don't want that. Once you've cooled the test tube and added the furan, you're going to stopper it, wrap it with parafilm wax, and then set it aside for a week to react. The procedure says that you need to be very careful about making sure the test tube is at room temperature before capping it, and that is because ether vaporizes at a very low temperature, and producing gas in a closed system is dangerous. Best case scenario, the stopper will pop off. Worst case scenario, the test tube glass cracks and explodes, and we definitely don't want that, so be sure that your test tube is completely cool. In the second part of the lab, we are going to look at the UV absorption of different sunscreens by putting them on a TLC plate under UV light. This is what the UV lamp setup looks like. Notice that the lamp is pointed downwards in the setup. If for some reason you have to move this setup around, just be careful that the lamp is off when you do that. It's very dangerous to look directly at the UV lamp while it's on. This is what a TLC plate looks like under a UV lamp. The plate glows green. When there are UV absorbing compounds on the surface of the plate, those areas of the plate will appear dark. And you'll notice on this plate there are some dark spots where UV absorbing compounds are. This plate is from a different lab. The UV plate is coated with a phosphor. So when the UV light hits that phosphor, it's absorbed, and then it is re-emitted at a lower energy wavelength. In this case, it's emitted as green light. If a molecule is on the surface of the plate that does not absorb UV light, such as this alkene here, the UV light will pass right through, hit the phosphor will still emit the green light. So in a sense, this compound is invisible on the plate. However, if a UV-absorbing compound is on the surface of the plate, such as this conjugated alkene here, before the UV light can get to the phosphor, it's absorbed by that compound. So if the UV light's not absorbed by the phosphor, no green light is being re-emitted. So that particular area of the plate appears dark. This is exactly how sunscreens work. The sunscreens sit on the surface of your skin. They absorb the UV light before the UV light can penetrate your skin and cause damage. In the final part of the lab, we are going to use UV-vis spectroscopy to investigate different forms of a chemical indicator. UV-vis is plotted as wavelength versus absorption, and we're primarily comparing the peak wavelength absorption between different molecules. As you can see in this example, the greater the extent of the conjugation, the longer the peak wavelength absorption. And longer wavelengths are corresponding to lower energy. You should be familiar with the relationship between wavelength frequency and energy difference from lecture class. The more conjugated a molecule is, the longer the peak wavelength absorbance will be. Longer peak wavelength is going to correspond to a lower frequency and a smaller energy difference. In the case of conjugated molecules, the energy difference we're talking about is the difference between the HOMO and LUMO, which would be the pi to pi star transition in terms of orbitals. If a molecule has a lot of conjugation, it's possible that the wavelength could be in the visible region. If a molecule absorbs in the visible region, then that molecule will appear colored. Here we have an example of 3 molecules that are increasing in conjugation. The pink line is naphthalene, the green line is anthracene, and the blue line is tetracene. You notice that naphthalene and anthracene are not absorbing beyond 400 nanometers. That means that all of their absorption is in the UV region. These 2 compounds appear colorless. However, tetracene, although its peak wavelength is in the UV, does absorb in the visible region between 400 and 500 nanometers. So tetracene, which is absorbing visible blue light, appears orange, whereas the other 2 appear colorless. The blue light gets absorbed, and the color it appears is opposite that on the color wheel. We'll be investigating a different indicator in lab class. However, you're probably familiar with phenolphthalein from your Gen Chem class. Phenolphthalein appears colorless below pH of about 8 and magenta above pH 8. The reason for the color change has to do with a structural change. You notice that the colorless version of phenolphthalein has a tetrahedral carbon at the center. So we have different benzene rings that are all conjugated, and they're also conjugated with some of the oxygen molecules in the carbonyl. However, those 3 rings are not conjugated to each other. However, as the pH increases, the molecule undergoes a structural change. You notice that we lose some hydrogens, and that tetrahedral carbon in the center is now an alkene, sp2. All the rings are now conjugated, and the peak wavelength absorbance is going to shift to longer wavelengths. So whereas the colorless form is absorbing only in the UV, the colored form of the indicator is absorbing around 553 nanometers, which would be green. Because it's absorbing the green, the indicator appears magenta. And this is essentially how all indicators work. So you will be investigating an indicator with UV-Vis spectroscopy. No matter which cuvette you use, make sure that you wipe down the sides of the cuvette thoroughly with a Kim wipe. And if you are using a plastic cuvette with frosted sides, be sure as you place the cuvette into the machine that the light beam is going to pass through the clear sides of the cuvette.